rotation of a complex number. This is a very important concept. So why do we use the rotation? So basically, let's say we have the any okay, so let's say we have the any complex number, let's say represented by this is, let's say a is complex number is z1, and let's say b point is represented at, let's say z2, and let's say some complex number is z3 represented by, let's say abc. So essentially, if we want to find the relation between z1, z2 and z3, then we use the rotation of concept. So basically rotation is helpful to, basically it is helpful to find relation between z1, z2 and z3. Okay, relation between z1, z2, z3, that is maybe z3 is something, let's say k times z1 plus z2. This is how we find this relation using the concept of rotation. Okay, one more thing associated with the rotation or any complex number, we said that in the previous lectures, complex number can be treated as a vector, 2D vector. So if you understand, if you know the concept of vector, so we can easily solve the problem of complex number, and rotation is one of the concept. See, let's say we have any, let's say any vector a b, okay, and let's say this is c. So I can write this is z1 complex number, z2 complex. So vector wise, this is vector ab. This is same as the z2 minus z1. In vector we call it ab, and in complex number we call z2 minus z1. And similarly we have the ac. AC is let's say here z1, z2, this is z3, is z3 minus z1. Okay, this is the corresponding vector and the complex number. Now these two vectors are not equal. So vectors are equal when they have the same magnitude and same direction. So vectors are not equal here. So vectors are equal only if we have the directions are same and the magnitude are same. Okay, for they have the same magnitude and direction, both are same, then only we call these two vectors are equal. But these vectors are not equal. Okay, but we can say that about these vectors a b c, direction is anyway different, but magnitude wise we can make them equal. How? Let's say the magnitude of basically if we talk about the magnitude, so let's say we talk the vector ab divided by the magnitude of ab. Similarly vector ac divided by the magnitude of ac. Now essentially these two vectors are not equal. Why? Because their direction are different, but they have the same magnitude. Okay, same magnitude, because they have turned out to be a unit vector. Why they are same magnitude? Because they are the unit vector. Unit vector means the magnitude is 1. So even though these vectors are not equal, but their magnitudes are same. So these two vectors has equal magnitudes. So essentially if we want this vector ab should be equal to ac, so what should I do? So the now if I say that let's write like in terms of the complex number, or let's say first talk in terms of let's talk in terms of the complex number z1, z2, z3. If I say that the z2 minus z1 upon z2 minus z1 and z3 minus z1 upon z3 minus z1, these two complex number have the same magnitude, the modulus is same but not the direction. How can we make them equal? So we'll rotate the ab. If we rotate the ab by angle, let's say theta, then we turn out to be ac. So magnitude is not same, magnitude is same but not direction, so what should I do? So but not direction. Okay, what we have to do for making direction equal, or making for aligning these two vectors, or for making direction equal, we can say, for making direction equal, rotate this vector, rotate this AB vector, AB by angle theta anti-clockwise direction. So if we rotate AB by angle theta, we turn out to be AC. So I can say the magnitude wise this vector AB, AB unit vector, and this is AC unit vector. If we rotate AC by theta, then we turn out to be AB. So magnitude wise same, magnitude of AB unit vector, magnitude of AC unit vector same. But if we rotate, if we let it rotate by theta degree anti-clockwise, then they are same. Because see, this vector has this vector we'll rotate the okay, rotate AC, we have to rotate AC by, and okay, just a minute. So we'll rotate the, not AC, rotate the AB vector, rotate the AB vector by theta in anti-clockwise direction. So then the AC unit vector will be AB unit vector, this one. So what I mean to say that when the AB vector is rotated by theta, we'll get AC. So this is the AC is the unit vector which has direction along the shown. If we rotate AB, so AB magnitude wise same, but not the direction. But if I take complete these things, so AB and the rotation by angle theta, then they are same. Got it? Now this is turned out to be a AC unit vector. And same way in terms of the, so in terms of the complex number, we can say that, and we'll see how it is happening. Let's say this is Z1, Z2, and let's say Z3 theta. So I can say Z3 Z1 divided by Z3 minus Z1 is equal to Z2 minus Z1 upon Z2 minus Z1, then rotate by theta, rotate by theta. That rotation by theta in complex number is nothing but e to the power I theta. So essentially Z3 minus Z1 upon Z3 minus Z1 modulus, the magnitude, is equal to Z2 minus Z1 upon Z2 minus Z1 e to the power I theta. Got it? Now they are equal. Now they are equal. So we can say this is equal. This is very important rotation. We can say formula, or it's not required to formula. It's basically a relation. We can easily find out. It's not a very rocket science, because just what we have done, the magnitudes are equal. Now we rotated by e to the power I theta, we get the rotated vector. And we can see why it is happening also. We can quickly see why it is happening. See, any vector, let's say this is Z1 and this is Z2. Let's see this theta. So I can say that the Z2 upon magnitude of Z2 is nothing but Z1 upon magnitude of Z1 e to the power I theta. So if the Z1 vector or Z1 complex number is rotated by theta, that is multiply e to the power I theta, we get the vector or the complex number Z2. And we can see why it is happening. See, let's say this has alpha, so we can say that the let's say this this is magnitude wise 1, so we can say Z2 by Z1 is something 1 e to the power I alpha plus theta. And what is Z1? Z1 is also magnitude is 1, and its argument is e to the power I alpha, and then e to the power I theta is multiplied. So I can say the e to the power I alpha plus theta. So now we can see that these are equal. So rotation by e to the power I theta, they turn out to be a new vector or new complex number Z2. Okay, so exactly same as the vector. So the way we treat same as the vector also. So if you want to solve the problem vector, we can also use this concept. Let's say A, B, C, this is let's say theta. So I can say that the AC unit vector is AB unit vector e to the power I theta. This is a very important relation. You need not to memorize, you understand why I am getting this one. Okay, in terms of the, let's say this is the Z1, this is Z2, and this is Z3. In terms of the complex number, I can say that the Z3 by Z1 upon Z3 minus Z1 is equal to Z2 minus Z1 upon Z2 minus Z1 e to the power I theta. Mind is theta is the rotated anti-clockwise, otherwise it will be negative. Okay, so why rotation is useful? Rotation is useful, so basically rotation is useful for, so now why rotation is useful? Clearly the rotation is useful to solve the 2D geometry problem, okay, in complex numbers. So why rotation? So basically I can say that the rotation concept which I have just explained before. So rotation, this is useful to solve 2D geometry problem, okay, to solve 2D geometry problem using complex number. This is how we use the rotation. So again I am emphasizing, so let's say this I discuss this is, let's say, z1 vector or z1 complex number, and the angle is, let's say, theta, and if I ask you what is z2, so z2 will be z1 e to the power I theta. Okay, let's say divide also, otherwise z2 z1, and let's say if I want somewhere clockwise, if I rotate something, let's say this is z3, this is angle is alpha, so z3 we can say that z3 by z3 is equal to z1 by z1 e to the power minus I alpha. That's the important thing. Okay, ठीक है. Now let's talk about the application. Let's talk about the application of the this concept. This is very much useful. So in the complex numbers, let's talk about the application of this rotation principle, application of rotation concept. So application of the rotation concept. Okay, let's take a very basic concept. We'll see what this concept is, but let's say we have any complex number is written like, let's say this is a point has a complex number z1, let's say point B having complex number z2, and let's say this is point P having complex number, let's say, zp, and let's say this point P divide a b m is to n ratio, and let's say we have to find what is the complex number zp. So we can say that you can clearly see that the AP upon PB is nothing but m by n. This we can clearly see. And what is AP? I can say AP is ZP minus Z1. This is AP. And then BP. BP is Z2 minus Z1. Z2 minus ZP. Okay. Now they both have the same direction. This vector AP and PB, they are in the same direction. The AP and the PB are in the same direction. So essentially direction is same. We have to just make the magnitude equal. So I can say that the this AP vector upon AP is same as the PB vector upon PB. So using this, I can say that ZP minus Z1 upon magnitude of ZP minus Z1 is equal to Z2 minus ZP divided by magnitude of Z2 minus ZP. So essentially what I will get is ZP minus Z1 upon Z2 minus ZP is ZP minus Z1 magnitude upon Z2 minus ZP. So ratio. So ZP minus Z1, ZP minus Z1 is this and this. So the ratio is nothing but m is to n. Okay. Now if we solve, so solving we get, so we can simply solve it. So just okay, let's solve it quickly. So what was that? Zp minus Z1 upon Z2 minus Zp. Good. So we'll solve it. This Zp minus Z1 upon Z2 minus Zp is equals to m by n. We can clearly see that n Zp minus n Z1 is equal to m Z2 minus m Zp. So we can take the common as Zp. Zp n plus m is nothing but m Z2 plus n Z1 divided by m plus n. So essentially Zp is m Z2 plus n Z1 upon m plus n. So clearly if any this is, let's say, Z1, this is, let's say, Z2, and the point P, the coordinate of point P, which divides this line AB in m is to n ratio. M is to n ratio. Then the coordinate of Zp is given by this formula. Okay. So this is, this particular things here is a well-known section formula. This is called a section formula. In the complex number this also exists, in vector also. This is nothing but the section formula. Okay. Okay. Let's take one more example. Let's take one more example. Let's say we have this particular complex number. Let's say this is Z3 and this is Z4, and let's say this complex number is, let's say, Z1 and let's say Z2. So we have to find the condition or relation. If I ask you a very basic question, what is the condition or relation for perpendicularity of these two segments? Okay, we have to find the condition. We have to find the condition for segment. Let's say this segment is A, B, C, D. Condition for AB segment and CD segment perpendicular. What is the condition for these two segments perpendicular? So clearly this is, let's say, vector AB, and this is vector, let's say, CD. Okay, so they are rotated by angle pi by 2. So can we say that the AB means rotation? So Z1 minus Z2 upon Z1 minus Z2. If I want this vector Z1 minus Z2, then we have to rotate the Z3, Z4 AB vector by 90 degree. So I will say it's rotated by the 90 degree. So I can say that this is the rotation vector is Z4 minus Z3 upon Z4 minus Z3 e to the power I pi by 2. So they are rotated by e to the power I pi by 2. Got it? This is the condition. Okay. And if you simplify, I will get Z1 minus Z2 upon Z4 minus Z3 is equal to Z1 minus Z2 upon Z4 minus Z3 magnitude wise e to the power I pi by 2. See, if we simplify this part, we'll see that this is a real number and e to the power pi by 2 is I. So I can say it's nothing but I into the pure real number, because modulus is a pure real number. So essentially, if Z1 minus Z2 and Z4 minus Z3 complex number are perpendicular, if, see, I into pure number, that means this is nothing but pure imaginary. Okay, pure imaginary number. So essentially we can say that the Z1 minus Z2 upon Z4 minus Z3 is pure imaginary number. It's a pure imaginary number. It's a pure imaginary number. So that is a pure imaginary number. So essentially we can say that a very basic concept, that ratio of complex number. So this is one complex number, Z1, Z2, another complex number is Z3, Z4. They are perpendicular if they are purely imaginary. So I can say that the ratio of complex number. What is the ratio of complex number? That means Z4 minus Z3 upon, let's say, Z2 minus Z1. So ratio of complex number of perpendicular segment, these segments are perpendicular, is purely imaginary. That's interesting. This is purely imaginary. Okay, so it's purely imaginary. So any ratio, it can be taken as Z3 minus Z4 upon Z1 minus Z2, or Z4 minus Z3 upon Z2 minus Z1, uh, or ठीक है, Z4 minus Z3 upon Z1 minus Z2, all are purely imaginary. Purely imaginary. Okay, ठीक है. Okay, so let's take one more example. Let's say these two complex number are parallel. So let's say this is A Z1, B Z2, and the other complex number is let's say C Z3 and D Z4. Let's these two complex number are parallel. If they are parallel, so what is the condition? So again we can say that since they are parallel, the direction is same, only magnitude are different. So I can say that the Z2 minus Z1 upon mod of Z2 minus Z1 is equal to Z4 minus Z3 upon Z4 minus Z3. Okay, both are unit vector. So these are magnitudes are equal because direction is already same. Two vectors are same if their magnitude as well as direction. Since the direction is already same, to make the magnitude equal, we will convert into unit vector. So these are same. So essentially what we get the ratio is Z2 minus Z1 upon Z4 minus Z3 is mod of Z1 minus Z2 upon mod of Z4 minus Z3. This is purely real. This is purely real. Okay, so I can say Z2 minus Z1 upon Z4 minus Z3 purely real. So what conclusion we can draw from here is that if the ratio of two line segment are purely real then line segment will be parallel. Line segment will be parallel. Okay, so these are conditions for two line segment to be parallel. Okay, let's take one more example. To understand better, basically this is used to find the relation between the different complex number. So let's take one example. Let's say Z1, Z2, Z3 are vertices of isosceles triangle. Right angle at Z2. Then prove that prove that Z1 square plus Z1 Z2 square plus Z3 square is equal to Z1 Z2 Z1 plus Z3. Okay, so essentially let's say these are the triangle, let's say z1, right, z2, we'll draw the z2 here. So z1, z2, z3, these are pi by 2. So they are isosceles triangle. Isosceles triangle, that obviously these and these are equal. So what we can draw, let's see, these are equal and pi by 2. So magnitude wise I can say that the z1 upon z2 upon mod of z1 z2, this is this one, and z3 minus z2 upon z3 minus z2. And since this vector rotated pi by 2, so I will write e to the power I pi by 2. And since these magnitudes are equal, I can say z1 minus z2 is equal to z3 minus z2. So I can say that the z1 minus z2 is equal to z3 minus z2, e to the power I pi by 2 means I. And since this we have to prove here there is no term I, no, because, so there is no I or imaginary part, so we will square it. After squaring I get z1 minus z2 square is equal to z3 minus z2 square I square. Okay, so essentially we'll get z1 square plus z2 square uh, minus 2 z1 z2 is equals to I square is minus 1, so z3 square plus z2 square minus 2 z1 z2 z3 z2, and then I square is minus 1. Okay, so what we'll get, z1 will get z1 square plus z2 square minus 2 z1 z2, and then minus 1. So essentially it will be 2 z3 z2 minus z3 square minus z2 square. Okay, so we can simplify here. So I can say that taking that, so z1 square plus z2 square and z3 square left hand side plus z3 square, and so 2 times 2 z2. Achha, by the way, this is here it's a 2, and here also then it will be 2. So 2 z3 square is equal to okay, so I will take z2 is taken common and z2 is also taken, 2 is taken common, and z2, so it will be z3 plus z1. I think this way to prove, yeah, this way to prove. So this way we are able to prove this particular relation between z1 z2 z3 using the concept of rotation. Okay, let's take one also very basic example. Let's say if area of a triangle, formed by let's say z I z and z plus I z, okay, is 8, then find the value of, let's say, find magnitude of z. So essentially how does look like, if somewhere is the, draw it, somewhere is the z, and since I is multiplied, I means e to the power I theta, see, I means e to the power I pi by 2, so z is multiplied e to the power I pi by, that means it rotate this vector to a 90 degree, this is 90 degree, this is I times z, and z plus iz, what does z plus iz look like? So z plus iz is nothing but we have discussed the addition also, so this is somewhere along the diagonal, so this is z plus iz. Okay, so this is this is, so essentially we have this we can say this is Z, so this is Iz and this is Z plus Iz. So obviously this is 90 degrees, so this is also 90 degree, and this is, since vector, in mathematics we treat vector as a free vector, same with the complex number as free vector. So this Iz is also same as the Iz here also. Okay, magnitude wise also this magnitude is Z, and this magnitude is also the magnitude of this particular thing is this also Z, because because Iz magnitude means magnitude of I into magnitude of Z. Magnitude of I is 1, so essentially it is a magnitude of Z. So what the area of this triangle is nothing but half Z into, so half base into height, Z is square, that is 8. So what is Z here? 16. So Z here is plus minus 4, but Z is a magnitude, it's a positive value, so essentially Z will be 4, not minus. So this is the answer, the magnitude of Z will be 4.